Okay, welcome to part two. At this point, we're going to talk about Earth-Sun relationships and why it is that we experience changing seasons. Now, the basic answer to that question is because the Earth is tilted. It's tilted 23.5 degrees away from the vertical as it goes in its orbit or revolution around the sun. What that does is that produces variation in sun angle and day length at different parts of the world at different times of the year. Well, why is sun angle so important? You can demonstrate this in the classroom with what I call the flashlight model, and everyone's tried this at one time or another. Okay, go into a room with your flashlight, turn off the lights, and then shine the flashlight down onto the desk at a 90-degree angle. All right, now if you're with kids, you can ask them what does the light look like on the table, and then they'll tell you that it's a circle. And then what you tell them is what you're going to do is just change the angle of the beam. You're not going to take it further away or turn it down to low beam or anything like that. All you're going to do is just change the angle. Well, if you move the angle down to, let's say, 45 degrees, and then ask them, what does the light look like on the table? And then they'll say, well, it got bigger, or now it's a large oval. And so what that means is that at a lower sun angle, you spread that radiation out over a larger surface area. When the beam is a 90-degree beam, that means that it's a concentrated beam. So you're building up a lot of heat on the Earth's surface. Whereas when the sun angle is coming in low, say as in the winter season or near sunrise and sunset, when the sun's coming in low, it doesn't generate as much heat because it's spread out over a greater surface area. All right, so low sun angles spread insolation out over a greater area. High sun angles mean that you have a greater concentration of insolation over a smaller area. All right, so we have more intense solar radiation when the sun angle is more vertical. All right, now we're ready to take a look at the seasonal changes during a typical Earth year. So what I have here is all right, this is the textbook's figure of the globe. Notice that the tilt doesn't change. The Earth doesn't go back and forth changing its tilt. It's always tilted 23.5 degrees away from the vertical, always pointing at the same thing, Polaris, the North Star. Well, what does that tilt do as you go around the solar system? Notice that on this side of the solar system, so it's labeled June 21st, that's the summer solstice in the northern hemisphere. Notice how the northern hemisphere is kind of leaning into the sun. Well, that means we're getting our highest possible sun angles at that time of year. Whereas when you come over here to this time of year, December 21st, that's the winter solstice in the northern hemisphere. Notice our hemisphere is kind of leaning away from the sun. Something else to see, we'll come back here over to June 21st. Notice with our hemisphere kind of leaning into the sun, that you look up here at the North Pole, it's in continual daylight. Well, what that means, if you could use your imagination and spin this globe around, we would spend here in the northern hemisphere, here at the latitude of Pembroke, we'd spend more time on the lit up side than the darker side. And so that's another reason for the seasonal contrast. You have, besides having higher sun angles, you spend more time on the day side, so you have longer days for heat to build up. Conversely, over here in the wintertime, use your imagination and spin that globe around. Now, here, if you're anywhere above the Arctic Circle, if you're here up at the North Pole, you're not going to see a sunrise on that date. So we spend more time on the dark side than the lit up side at that time of year. All right, so one of the things that we need to do, we need to take a look at the characteristics of the summer solstice, the winter solstice, the spring equinox, and the fall equinox. For us in the northern hemisphere, I think is a good thing to know. And then also explain why the seasons are reversed in the southern hemisphere. And indeed, they are. When we're having summer, they're having winter. Matter of fact, what season is it right now in the southern hemisphere? I'm going to take a look at a more specific diagram. This one's not in the textbook, but I put it in the online notes. I like this one because it has the geographic grid on it, whereas your textbooks did not. I think it's a little better for understanding this. All right, let's take a look at the characteristics as we go through a typical solar year. You could start anywhere because it's a continuous cycle, but let's start over here at the time of the June solstice, which is the summer solstice in the northern hemisphere and the winter solstice of the southern hemisphere. Now, for each one of these diagrams, you've got to ask yourself, where are the vertical rays of the sun? Well, the vertical rays of the sun, the 90-degree rays, are on the Tropic of Cancer at 23.5 degrees north. And that's the reason why that is a tropic line, the Tropic of Cancer. Because that's how far poleward the vertical rays of the sun reach during a typical year. You have to be within the tropics in order to have the 90-degree sun angle above you with the sun directly overhead. Can the sun ever be directly overhead in Pembroke? No, because we're not within the tropics. Okay, and so if we look at some other characteristics, notice that the sun's rays shine over the pole to a latitude of 66.5 degrees north. Well, that's the Arctic Circle, and that's the reason why that is the Arctic Circle. Okay, where the Arctic starts, the number just wasn't pulled out of a hat. That's because that's how far over the poles the sun's rays reach at the time of the solstice. And also using your imagination and make that globe spin around, we spend more time on the lit up side than the dark side. So not only we're leaning in and having our highest possible sun angles, but we're also having longer days. Now, the day length at the equator is always 12 hours day, 12 hours night. But you get more and more seasonal contrast the higher you go in latitude. For us in Pembroke, well, the longest days of the summer are probably something like 14.5-hour days, but it gets more extreme the further north you go, getting into Minnesota, 18-hour days, till eventually, if you get above the Arctic Circle, at the time of the solstice, you're in perpetual daylight. One of the reasons why they call Alaska the land of the midnight sun is because there, above the Arctic Circle, you're in continual daylight. So it's more extreme. The closer you go towards the pole, you have longer and longer days. If you're at the North Pole at the time of the June solstice, you won't see a sunset. Conversely, if you're at the South Pole, or if you're anywhere south or poleward of the Antarctic Circle, you won't see a sunrise. All right, well, after this day, this is the longest day of the year. They say that on TV and radio. But after this day, actually the days start to get a little bit shorter. The days are still longer than the nights, but the days are getting shorter and shorter and shorter until we get to this point which is the September equinox. This is the fall equinox in the northern hemisphere and the spring equinox of the southern hemisphere. Where are the vertical rays of the sun? Well, the arrow is a perspective diagram here, but the vertical rays of the sun are on the equator. Well, what are the day length hours like for us? Well, we have exactly 12 hours day, 12 hours night at the time of the equinox. Well, how about at the Arctic Circle? What's 12 hour, 12 hour? How about at the Antarctic Circle or the Tropic of Capricorn? Well, 12 hours, 12 hours. So everywhere on Earth has a 12-hour day and 12-hour night at the time of the equinox. So it's equal night. All right, well, after that point, the days are shorter than the nights. Shorter and shorter and shorter until we get over here to the December solstice, which is the winter solstice in the northern hemisphere and the summer solstice of the southern hemisphere. Notice the daylight characteristics here. We spend more time on the dark side. At the latitude of Pembroke, we get something like about 9.5-hour days, and the longest day is at the time of the December solstice. And so with those short days, and it gets even more extreme, the higher and higher you go into the latitude, till eventually, when you're poleward of the Arctic Circle, you don't see a sunrise. Okay. All right, and so where are the vertical rays of the sun? They're on the Tropic of Capricorn at 23.5 degrees south. And that's the reason why that is the Tropic of Capricorn. All right, and then after that, actually after the solstice, the days start to get longer. Now, the days are as short as they're going to be, and they're still pretty short, but the days start getting longer and longer and longer till we're here at the March equinox, which is the spring equinox in the northern hemisphere and the fall equinox in the southern hemisphere. Where are the vertical rays of the sun? They're on the equator. What's the daylight conditions like in Pembroke? Well, 12-hour day, 12-hour night. What about the Tropic of Capricorn? Well, 12-hour day, 12-hour night. What about the Arctic Circle? Well, 12-hour day, 12-hour night. Okay, so everywhere has equal day and equal night. That's the equinox. All right, and then after that, the days start getting longer as we head back to the solstice again. Some cultures celebrate May Day, May 1st, when you're exactly halfway between the equinox and the solstice. And that's kind of a pleasant time of year, I think, in this climate. It hasn't gotten too hot yet. All right, so as we go through a typical year, the sun angle changes. We get our higher sun angles in the summer, thus generate more heat at the surface. And then longer days also generates more heat. Are the seasons reversed in the southern hemisphere? Yes, they are. When we're in summer, they're in winter. Well, how about in Australia? What do they do about Christmas? Well, they still have Christmas on December 25th, but in Australia, Christmas is all about outdoor pool parties and the like. It's not riding in the snow in a sleigh. Okay, this is another one of the diagrams from your book that shows you that here in the northern hemisphere, we spend more time on the lit up side than the darker side. What if Earth didn't have any tilt? Because that's the answer to the question, why is it that we have changing seasons? It's because the Earth is tilted. If we didn't have any tilt, there wouldn't be any seasons. You would just be warmer or colder depending on where you are in latitude. but we do have a tilt. Well, what if it was tilted more? Well, if it was tilted more than 23 and a half, we would have even greater seasonal contrast. Our summers would be more intense and hot, and our winters would be colder. Okay, so it's because that tilt combined with revolution around the sun produces variations in sun angle and day length at different times of the year, at different places, and so we have seasons. You know, the word tropic means to turn. And in this diagram, I like how it shows that the vertical rays of the sun migrate back and forth between the two tropics. Okay, here we are at the time of the June 21st solstice. The vertical rays of the sun are on the Tropic of Cancer. And then after that, I'll come in back on this side, where the vertical rays are back to the equator. And then the vertical rays go down to the Tropic of Capricorn, and then the vertical rays go back to the equator again. So the vertical rays go up to the 23.5 degrees, they turn, they go back down to the equator, they go back to 23.5 degrees south, they turn and go back to the equator. So tropic means to turn. All right, and the sun can never be directly overhead in Pembroke. The highest possible sun angle for us is something like 78 degrees above the horizon.